Stable Diffusion, a very impressive image generation model, perhaps comparable to DALL-E 2. All the images you are actually seeing right now are coming straight from Stable Diffusion. I'm sure many of you have already seen or heard about this. It has absolutely blown up recently with plenty of people talking about this. And so as to not beat a dead horse, I was hoping to do something a little bit different in this video. Now, I will briefly explain how Stable Diffusion works and also why it has, well, so quickly gained this massive following, but we will be doing also quite a bit more. For one, I want to directly compare DALL-E 2 and Stable Diffusion. Now, lots of people have been talking about how Stable Diffusion is around the same, or at least comparable to DALL-E 2 in quality. That claim, however, is never actually touched on in the research paper. So instead, I want to do a direct qualitative comparison in this video. Now, even more than that, I still want to go deeper. Specifically, we will also be going to the code in this video and seeing, yes, how you can use Stable Diffusion for yourself. Now, plenty of people have already done that too, so I want to go even beyond that and show you how you can extend Stable Diffusion beyond what's just in the starter notebook. And by the end of this video, I plan on showing you how you can even recreate something that, at least I think, is really cool that's been making its rounds on the internet, and that is this ability of Stable Diffusion to do this image-to-image generation where you start with an image and then you go and transform it into a much better image, but still something similar. And that's what you're seeing on screen right now. So I know that is a lot, but I think I can fit a lot into this video. Although there's a lot to talk about, I have lots prepared. So if that's something you're excited for, stick around. One last thing I'll mention before we get started is that I do cover a whole lot on this channel, from bigger papers and ideas to keep you up to date with what's going on to, well, also smaller ideas to, well, introduce you to smaller and niche ideas that I think are pretty cool. So if that's something that interests you, do consider subscribing. It really does help out the channel and I super duper appreciate it. So with that out of the way, let's now jump into this paper. We're going to touch on this just very briefly before we jump into the code and some examples. So the one thing I really want to touch on here, because this paper is, well, to be honest, it's not too different from your standard diffusion model paper. They do have lots of details about how the model works and stuff like that, but it is very similar to actually most previous diffusion methods. There's one big difference, and this is what I was looking for right here on the right. And maybe before I go into this diagram specifically, I'll first tell you a bit about how diffusion generally works using this animation I had for a previous video. So generally the idea for diffusion is that you want to, at least for training, start with an image and then step by step you add noise to this image. So you end up with a bunch of images that, progressively get noisier and noisier until you end up with, well, pretty much nothing but pure noise. Now, up until this point, everything is just done programmatically. There's no AI involved. You're just adding noise to an image. But after this point, once you have your fully noised image, this is where the machine learning comes in. The idea is that you want to take these noisy images and use a model to undo the noise of a single step. Then you can reapply this model for each individual step and hopefully slowly try and recreate this image that you originally had by slowly getting rid of the noise step by step. Now, of course, in practice, lots of the time, you're not going to actually be getting back the original image, but this sort of training still works very well. So now going back to this paper, what's different here? Well, what you see, maybe I should point out what's the same first. This is going to be our original image. We're going to ignore the E for a second. And then what you see is that this goes through the diffusion process, which is the process I just talked about of noising the image, adding noise to the image step by step. And then on the way back here, what you see is the opposite of that. This is the UNet. This is the model being applied to denoise the image step by step and then end back with hopefully the original image. So you try and match these two right here. Now, what is different in this model? This model, actually, it's not too different, as I had mentioned, from everything else. It just adds two extra things, an encoder and a decoder. And the idea here is that you're not feeding the observation directly into the diffusion process. And the reason for this is because working with these giant images, a 512 by 512, or even worse, a 1024 by 1024 image, that is very expensive. That's a lot of pixels to work with. So what they found in this paper is that if they actually use an autoencoder to first encode the image into a latent space, which is this Z right here, and then do diffusion all in that latent space, and then at the very end, use the decoder to get back the predicted image, that works. It doesn't get you better quality, but it's a lot faster, which is very nice. And that leads into the one more thing I wanted to talk about before we get into the code, which is why this has blown up so much. And it really comes down to 4 different core things. So the first thing is just that this paper has good results. This is the best I can write with my mouse right now. I'm pretty impressed. I think it's actually better maybe than when I'm using my tablet. But anyway, the paper has good results. They're not like state of the art for most things, but they're pretty good. The second thing, and this is a huge one, it's free. Yes, that is is right. It does not cost to use this, and that leads directly into the third thing here, which is that it's open source, which means not only can you use it, but you can also modify it, work with it. They have completely open source, not just the code, but also the weights, which means you do not have to do your own training, which training is by far the most expensive part of these models. So that's a very big plus. And finally, the fourth reason is that there are very low computational requirements to run this model. Now, I say low, they're not actually low, but they are low in comparison to what it would normally take. Normally, when you want to do one of these vision models, it takes just a massive amount of particularly GPU RAM, which is something that does not come cheaply. The average, consumer GPU card, I'm not actually sure. I can say that my GPU card though, which is a 1080 Titan, which is a bit of a dated card now, but it was pretty good when it came out, I guess. It's still pretty good. It's still pretty good, and it has 12 gigabytes of RAM. Normally to do this kind of thing, you would need much more than this, which means you're going to need multiple GPUs, or you're going to need to do something fancy that slows down the process a lot. But this works on consumer grade GPUs, which makes it very nice because you can just run it on your own computer, at least if you have a decent GPU. And I'll give you 1/5 and, a little bonus thing right here. I think lots of people are probably just happy that Stable Diffusion is kind of showing up OpenAI. People are saying this model is like, comparable, and it's free. And, on the other hand, OpenAI just released DALL-E 2 that is fairly expensive to use. It's closed source. So, it's always nice. Always nice to see someone going and really helping the community by open sourcing stuff and giving lots of resources for people to pick up this stuff. So kudos to Stability.AI. Now though, let us finally jump into the code and kind of dig deeper into this, see how it works, see how we can generate some of our own samples, and we'll eventually get to that DALL-E 2 comparison too. Here we are in a Google Colab. Now I will be linking this in the description, of course, along with a lot of other resources if you want to follow along yourself. And the idea is that I kind of have another notebook open on the side here. I'm going to be taking from my template and walking through the code with all of you step by step, going through each bit and piece of it. Even from the future here, I just wanted to come back and say, I almost forgot to mention, there is another notebook right here you can follow along with if you want. My notebook does cover this. This is provided by Stability.AI. I don't know why it's not loading. Oh, here we go. Yes, this goes into less depth than my notebook does. It has maybe more commenting and kind of explains the whole process better. I will mention my notebook does have a little bit of extra stuff we'll get into, but that is an awesome resource if you want to follow along with that too. That is also there for you. Now, the first thing we're going to need to do is just install a couple things. So Diffusers is a library from Hugging Face, is very new for diffusion models. It makes this very easy. We also need transformers because we need to encode the text, and then a few other miscellaneous things. So now that that's done, I just wanted to mention one thing I almost forgot. Make sure if you're doing this by yourself, you go up here to runtime and you change runtime type to GPU, because otherwise this is not going to be able to run fast at all on a CPU. So you want to make sure you're on a GPU. Then what we are going to do is just import a bunch of things. I'm not going to go through all the imports. This is really just doing everything at once so we don't have to come back and do it later. We are setting the device to CUDA, which means this will be on the GPU. And we also have to log into Hugging Face. You can just click here. If you don't have an account, it's super easy. You get an access token. You can then just come back here, paste in here, log in, and now we have access to extra Hugging Face features. And Hugging Face, by the way, is where we will be downloading the models from. So the next thing we are going to want to do is just add a little bit of code to load up the model. Now this alone will already load up everything we need. Now we will go back and we will do this more step by step to understand sort of what's going on and customize this a bit more. But for now, this will load the Stable Diffusion model version 1.4, which is the main model they recommend using, and then put it on the GPU. So let's run this really quick. And again, we're gonna have to wait a bit and I'll be back once this is done. Looks like I had an issue here. I'll probably just restart things. Usually this works. Give it a restart, and I'll be back once it's working. Okay, I got it working. I don't know what the issue was before. I just gave it another run. Didn't change anything. It's working now. It was probably just a bug on the server side or something. But now, oh, I put that there early. Now all we need is a prompt. So let me think of a prompt really quick. Maybe we want to do something like, I don't know, maybe a cute Shiba Inu dog. Inu dog. Who doesn't want to see that? They usually do corgis at OpenAI. We can show them up with a cute Shiba Inu. And now we want to put this here. So the autocast will essentially make this run a bit faster. I think it changes this to use like yeah, here it says float 16 instead of 32, minor details. But anyway, this pipe is what we just loaded up, and it is what is going to take our prompt, run it through everything, and eventually generate a sample image, which we will then display like this. So let's go ahead and do this. And we will see that this does take a little bit of time. Essentially what's happening right now is it's going to go through, by default, 50 steps of diffusion. Because remember, here we're just starting from, essentially, because we're not trained anymore, we don't need the input image. We just start from noise, and then go through these 50 steps of trying to go backwards, and out we should hopefully get an image here. Oh no, potentially NSFW content was detected. This is one issue. If you just either use their pipeline, it will block stuff like this. So let's run it one more time, and it is random, so we should get a different image this time. So hopefully one that's not, I don't know what it would have detected that would be NSFW, but hopefully this one works. Let's see. Incredible. So this is a little cutie. The color's a bit bright here, but you can see it's pretty good, for a model that you just downloaded in a couple minutes, you already got running. I guess this isn't on my computer. This is on Google servers, but that's fine. I could do this on my computer. I have. And there we go. That's really all it takes. So it's super easy to get running, but now can we dig deeper? What else can we do? So the first thing I want to do is something that will help us do this DALL-E 2 comparison. Now, if you've ever used DALL-E 2 before, you'll notice that when you put in an image, you get out, I think it's 3 images in response. So you don't just get one, you get a few options. So we can copy some code, and this is some code from the original notebook I mentioned earlier. I'm not going to explain it, it's just normal Python. It takes in images and displays a grid of images. And now we can do something like this. So I guess Shiba, maybe we should come up with a different prompt here. So what should our prompt be this time? Maybe we want to do alien, maybe alien riding a giant flying beetle in space. Is that how you spell beetle? Hold on, no. It's giant beetle in space. I think that's it. Hopefully it's right. Let's put an exclamation mark. Maybe that will make something happen. And then let's put digital art. That's a little trick. I'm not sure if I need a comma here. Who cares? Let's just give this a go. The only differences here, right, are that I am multiplying this prompt by 3, which will mean we have 3 prompts, which will mean this will generate 3 images. Then we pass our 3 images into image grid, and we should get out an image grid. The only downside here, right, is that this will take 3 times as long. So I'll be back as soon as this is done. There will be a lot of waiting when you're doing this yourself, unfortunately. Now, there are some things you can do that I will show you in a bit to make this faster. The quality will not be as good, but when you're experimenting, just trying to figure things out, it will be nice. So I'll be back in 1 second. Okay, here we go. Should be coming up any second. Oh, incredible. This is definitely interesting. So that's I'm not sure I'd call this a beetle. I don't know what it is. Maybe I guess it kind of has some beetle-like features here. It's like a beetle spaceship, maybe. I guess that could be an alien. And okay, so the results are mixed. This kind of I just really, this is like grabbing his hand or something and like pulling him along. Is this an alien child? I have no clue what's going on here. It's like he's holding a balloon, right? Is it just me? Anyway, results are mixed. This does clearly interesting, but I don't know. I don't know if it quite got the prompt. But now I want to do what I promised in the beginning, and that is going to be doing a direct comparison with DALL-E 2. Now we will be coming back to the code for a little bit of extra spicy stuff in a bit, but now that we have these 3 images, this is basically DALL-E 2's functionality, right? So I'm just going to take this prompt directly as is, and I'm going to go over to DALL-E 2, which I've already prepared, paste this here, and we are going to wait for our images. Okay, so, oh God. Oh my gosh, this is incredible. So for one, it was 4 images, not 3. My bad. I'm gonna say it. I think I see a clear winner here. This is only one example so far, but DALL-E 2 definitely has some interesting. It's clearly getting the prompt better, right? We clearly have an alien. We clearly have beetles in each of these. I will say the quality is very questionable. Um, I love this one on the right. This is so good. But let's try something else. So maybe something like, I kind of like these very like landscapey ones. So maybe we can do like, actually let's do a beautiful ancient forest full of magic and spirits. I think I need to correct this. And let's see what this gives us. And while that's going, I'm going to copy this and I'm going to come over to Stable Diffusion. We'll copy this here and we'll see what we get over here too. Okay, so here we go. So this is our Stable Diffusion. This is pretty good, I would say. Now, it does look somewhat, I'm not sure it looks ancient, definitely looks old. It is definitely a forest. I'm not seeing so much like, magic and spirits. I could imagine some magical stuff happening here, but it's not really too exact. Let's see if DALL-E 2 did any better. Okay, just finishing. Okay, honestly, I'm gonna say it's not super different. It does look like the quality is maybe a little bit less is what I want to say in Stable Diffusion, but that might also just be because we're blowing up the images a bit more. I guess when I said magic and spirits, it took it in a not very literal way, but I kind of wanted a more literal way. But I'd say this is about even. maybe slightly favoring DALL-E 2 here. There does look to be some nicer fine details, I think. But let's go with something. Let's challenge DALL-E 2. There is something I know DALL-E 2 absolutely is horrendous at, and that is anime characters. It cannot do anime characters for the life of it. Let's try doing anime character eating a burrito and see what happens. And by the way, I have not tried any of these before. I've tried this on a Stable Diffusion, but I haven't tried it on DALL-E 2, so I'm very curious what will happen. And we're going to try this here too. We'll be back soon. Okay, looks like we're about done. What are we going to get? Oh God, the middle one just got me. Oh my God, there's so much stuff happening here. This is true artwork. Maybe you should let me save this real quick. I I don't want to lose this one. Okay, I got that saved. Someone let me know in the comments if they want this too. Maybe I can post it publicly. So this is absolutely incredible. I don't know what's happening on this left one. Looks like we got a little story going on here, which is great. In the middle one, first of all, these hands. Oh Jesus Christ! I'm not. There's so many things wrong. What's happening with the hand? What's going on with the hair? Why is their hair turning red and into like a, I don't know. And I think like what are these things in the middle of his, is this like supposed to be Naruto almost? Like the little whiskers Naruto has? The mouth, the chin, just everything that could have possibly went wrong, I'm pretty sure went wrong in this one. And yeah, this isn't good either. The I wonder what it's trying to say here. Anyway, I wasn't expecting this to be too good, honestly. I for some reason, I guess there's just maybe not much anime training data. Something goes wrong when you ask it for anime. But to be fair, I think DALL-E 2 is not great at anime either. So let's see what it came up with. Okay, I'm gonna say this is much better than what I've seen it do previously with anime. If I still have, I have this hilarious image. I'll put it up if I still have it of something DALL-E 2 generated. But this is not. It's kind of anime, not really. It's not great. It's clearly better than Stable Diffusion. Every time I look at it, clearly better than this, right? So let's do one last thing. We'll do it real quick. I want to get back to the code soon, but I have one cool idea. So let's do like planet scale halo of water in space. I don't know, random thing. We'll add a digital art, and then maybe also trending on. I think it's supposed to be capitalized. Trending on art station. I think these are two little things of prompt engineering you can do to make your thing better. So let's generate that there, and then we'll go here again. This will be the last one. Then we will get back to code. I promise you all. Just about done generating. I have a feeling that they're both going to do pretty good on this. Okay. So the first one, I don't know what's going on here. The second one is kind of beautiful. I don't know what the text is, but this is like, I guess it's a planet, and then you have a ring of like a halo of water. That's interesting. And then I don't know quite what's going on here, but I guess, this could be water, kind of halo. Let's see what DALL-E 2 got. Now, okay, this is really good. Oh, DALL-E 2 is still amazing me quite a bit. I've used it a bit now. I got access a bit ago, but it still doesn't stop amazing me. Some of these generations are just so good. I will say it didn't actually get, I guess unless this is the water back here, and I guess there's lots of water on this planet, but we're not actually really seeing a halo of water. Maybe something down here. Again, this one on the left also doesn't really have a halo of water. This is the only one that I can see that kind of has that going on. So doesn't really get the prompt. I guess in this one, Stable Diffusion maybe has been getting the prompt a little bit better, but in terms of just quality, DALL-E 2 really is, I think, knocking out of the park quite a bit more. So I wanted to do this because I've been using Stable Diffusion. I've used DALL-E 2, and I've seen lots of people talk about how Stable Diffusion is at least comparable to DALL-E 2, and I think that's just not the case. There's a bit of a caveat here, though. While DALL-E 2 definitely does seem to have better quality, I think Stable Diffusion, you don't actually see it in the pipeline here, but there is, I can add like a num, I think it's num inference steps. Yeah, so there's an option. This is set to 50 by default. This means that 50 inference steps are happening, trying to denoise the image every time we want to generate a new image. Now, during training, it used, I believe, 1,000 of these. And during lots of the comparisons it does in the paper where they get really good results, I think they're using around 250 steps, which is a lot more. I have also tried that, and I haven't gotten the best results, but they are usually a little bit better, or maybe it's kind of hard to tell. So maybe if you use the right parameters and the right scheduler, which is something we'll get into, maybe you can get better results from Stable Diffusion. But at the very least, if you're going to be running this on just, your general GPU or on Google Colab, you're almost certainly going to be getting, I think, significantly better results with DALL-E 2. And that isn't to say anything bad about Stable Diffusion. The results are clearly pretty good, but I still just don't think saying they're comparable is, I don't know, I don't think it does DALL-E 2 justice, and maybe giving a bit too much credit to Stable Diffusion. My take, maybe a hot take, but I haven't seen anything like this yet, so I wanted to go ahead and do it. Anyway, now that that is out of the way, we can get back into the code. So now that we have generated, these pretty cool things here. Oh, I will make a few cells to start our new code. What we're going to do is we're going to make our own pipeline, and our own pipeline is going to be, customizable. We're going to be able to do more stuff. So the first step in making our own pipeline is loading our own models. Instead of loading the entire thing, we're going to have to load these models part by part. So first thing we're going to want to do is load the VAE. So this is the variational autoencoder, or the encoder that turns the image into, puts in the latent space and then converts it back into an image at the end of the whole process. We are also going to need a tokenizer. The tokenizer is used for, converting the text into tokens, which can then be passed to this clip text model, which is the text encoder, because we also need a text encoder to encode our text. So we encode the image and we encode the text. So that's what those two things will do. And then we need a UNet. So a UNet, you can look up what it is if you want. It's just essentially a type of model that kind of compresses something down and then blows it back up with some extra skip connections. No reason to get into the details of it now, but the UNet is what will do the denoising. It's once we actually have the latents from the VAE and from the text encoder, we will pass those into the UNet, and then that will predict what the noise is, so then we can remove that. And the last thing we'll need is not actually another model, but what is called a scheduler. And the reason we need a scheduler is something I'll get into a bit later, but for now, just know that it handles the process of going and doing the number of inference steps. And by inference steps, I mean denoising. It helps do those steps and make things clean. So we can go ahead and do this. And I'll be back in a second. This again, we're going to have to download these. So this will take a second, at least though these are also all pre-trained. So we won't have to do any training or anything. Once these are downloaded, we will be ready to go. So I'll be back after that. Okay, that took around 3 or 4 minutes to download. We are back now. Bit more calm down now. So we got, this is what we're going to do next. So now that we have all the models downloaded, we need to actually take the text that we're going to get in our prompt. This is the first step, right? We start with a prompt and we go from there. So we're going to take in a prompt and we're going to do a few things. So in this function, first we tokenize our text. So this will turn it into tokens. And then what we want to do is run that text through, run those tokens through the encoder, which will give us our embeddings. Now, after this, something a little bit weird happens. You would generally think, okay, we have our embeddings, we're good to go. We can throw that in the model now, right? Not quite. There's a little bit of a trick that happens here, and this is done with lots of diffusion models. I'm not super familiar with this, so just heads up, my explanation might have some flaws in it, but I think what this is doing, right? So they do this thing called, what's it called? Classifier free guidance, or maybe this is different. So this unconditional embeddings. So what they do is they take these embeddings for essentially the empty string, but then they expand them to be the same length as the actual prompt itself. So it's like a base, right? So if you don't have any prompt, this is like almost like the default. And what they do is they concatenate these together, the embeddings for the, what they call it, the unconditional embeddings and the text embeddings. And then we are going to end up using these, and I'll show you how we do that in a bit. But one thing we can do now is we can go ahead and actually test this. So for test embeds, we can say, maybe cute dog, we'll just do this because this is easy. So if we run this, what we will see is that we get some text embeddings, and if we print them out, you can see indeed we have embeddings of the shape 2 by 77 by 768. So this is 2 because we have 1 for the unconditional embeddings and 1 for the text embeddings. 77, I believe, is just the max length here. And then 768 is the dimensionality of the embeddings. So sorry if you haven't done like NLP stuff before and this is confusing. It's a bit much to go into now if I need to explain all of that. So I'm just going to skip over it for now, but I'm sure there are plenty of resources out there. So the next thing we're going to want to do is this producing latents function. So this is really the bulk of the work. What we're going to do here is take in the text embeddings. So these are going to be what we just produced, also along with a few parameters. So height and width are going to be the height and width of the model. I recommend 512 by 512. The smaller you make it, and if one of the dimensions is not 512, you're probably going to have some issues. just quality wise. Number of inference steps is how many times we're going to try and denoise the image. So generally the better, it's better when you do more of these, but it takes longer, right? The more denoising steps, the longer it will take. 50 is what they recommend. I found that 50 works pretty well. And then the guidance scale has to do with these unconditional embeddings. 7.5 or like 8 here is what's generally recommended. I'll talk about what this actually does. And then I have these latents here. And what is going to happen generally is we want to start, because we're just generating something from the prompt. It doesn't need to match a specific image, right? Which means we're just going to start with a random noisy latent space, and then we're going to start decoding it from there, which means at the very start of this process, the first thing we're going to want to do is generate, so torch.randin, this is just going to generate a random set of latents. And one thing I do here is I add the option to pass in custom latents. So maybe if we want to pass in the same latent every time to get the same output, because then there's nothing random, this is the only random part of this process, or there's some other uses we'll have for this later that I'll go and show you that will be pretty cool. So anyway, we produce the latents, put them on the GPU, and then we do this thing right here where we set the scheduler time steps. So the scheduler, now I'm going to try and explain what the scheduler is. Now I actually looked at the paper. I tried to find out about these schedulers. They're used in diffusion quite a bit, it seems. I guess everything in diffusion uses them. Tried to find papers, tried to find documentation. I could not find anything. So what I ended up doing is I just went to the code and I read through the code, and I think I understand what a scheduler is from that, but my understanding is probably not perfect. So if someone has a better explanation in the comments, I'd love to hear it. But here's my understanding. Essentially, when they're training the model, they do 1,000 diffusion steps. The issue is now when you're actually going to do the inference, we want to say, we don't want to do the full 1,000 steps. That's a lot. We want to be able to customize it based on the sort of fastness, is that even a word? The sort of speed versus quality trade-off. So we're using 50 inference steps here, right? So what we need to do is for each time we have our UNet predict what the noise is at each step, we need to scale that in a certain way such that at the end of these 50 steps, we end up with the end product. So the scheduler essentially what it handles is how to take the output predicted noise of this step from the UNet. So it's taking what the predicted noise for the step is, and it handles that and figures out how to scale it, how to apply it to our current latents to get the best results. That seems to be the case. We are using just sort of the default one they use in the tutorial notebook here, and it requires us to do a few things. The first thing it requires us to do is scale the latents by this sigma. I can't explain how exactly this specific scheduler works. So when we're like multiplying by sigmas and stuff, I'm sorry, I don't know exactly why this works. I'm sure there's some reasoning, I just couldn't find it. But that's in general what the scheduler does, I think. So next thing we're going to want to do is start this loop over these 50 time steps. And these will be our 50 diffusion. I think the word isn't diffusion, it's like undoing the diffusion, right? Our 50 inference steps. So we're starting with this random latent model. And what we want to do is, let's see what's happening here. So we're multiplying it by 2. This has to go in with the classifier free guidance stuff. Again, I'll talk about that in a second. Multiply it again, or we do some sigma stuff. So again, this is the scaling stuff. I'm sorry, I can't explain exactly why this works. Not all the schedulers require you to do this. I think it's just part of this scheduling algorithm that requires this. But then the two interesting things happen, right, is one, we use the UNet. So we pass in the latent data. We then give it the time step, and then we give it also, so this time step is coming from the scheduler, by the way, and then we give it the text embeddings. And what it will do is it will predict the noise. So not the next image, but it will predict the noise. And then what happens is the noise will eventually get fed into the scheduler along with the latents, and that will give us the next thing. So here you can see this is going from x of t to x of t minus 1, which is essentially undoing one of the noise steps. And then we are going to repeat this process 50 times, or at least if that's the value here, right, until we get latents and then output those latents. Now, you might have noticed I skipped over this here, and that's, I'll come back to that right now. So this is what's called classifier-free guidance, I believe. Hopefully I'm not wrong there. Essentially what's happening is you get the latents for the text embeddings that you gave the prompt for, and also these unconditional embeddings that we were talking about, which is just like an empty prompt. And I think the goal here is you take the noise prediction. So this is the noise predicted for the actual prompt, and this is the default, the empty prompt. You're taking the difference of the two, and then you're multiplying this, you're scaling that difference up a lot, and then you're adding it to the unconditioned noise. I think this says it helps it follow the prompt more, because you're essentially you're multiplying, you're scaling the difference between an empty prompt and the prompt you gave it, making it like kind of pushing it towards the prompt. I think that's what's happening. You can look up classifier free guidance if you want to know more. Anyway, that's what's happening there. Let's uncomment this and try this out and see if we get some, oh, test embeds. Oh, that's because I commented that out. So this will take some time, right? Because this is doing what was happening before. Now it's doing the 50 diffusion steps. And then at the end of the 50 diffusion steps, we won't quite get the image yet, but we'll get the final latents. And if you remember, so there we go, got our latents, and we also have the shapes. So this is good. We have one latent that is 4 by 64 by 64, and this is just the shape of the latents. So we can now go down one. I should recomment this out. We can go down here, and now that we have the final latents, what's the final step? Remember, it's to pass it through our decoder. So that's what we're going to do here. We take in the latents. Now there is some scaling stuff we need to do here. This is just because it's how they scale during training. We need to essentially reverse this. So we just do, I mean, it's just some scaling. There's really not much to speak about here. And then once we do that scaling, we can pass it through the decoder to get out our images. And now that we have the images, we essentially just need to rescale them, permute them so that everything's in the right order, and then scale them up to the 0 to 255 scale that you always use for images. And we can turn those into PIL images. And now that we have these images, we should be able to decode and hopefully see a cute dog. Yes, because that was our original prompt. So now we kind of have functions for all the main things that we're doing. So what we can do now is take these all together, put it all together and make a pipeline. So this is essentially the same parameters as before, and we're doing just the same steps. So we get the text embeddings, throw the text embeddings into the into the model to get the latents. Then we use the latents to get the, we decode the latents and get the images. So now what we can do is we kind of have, if you remember back up here, how we originally had this sort of a pipe where we just need to pass the prompt through it. We've essentially just recreated that. We pass in a prompt to our new function, and then it will take it through all the steps that we need. And we can do the cute Shiba Inu again. We can do something. I want to see another anime character. Let's do super cool anime character. I love the anime character earlier so much. Super cool anime character. Now, one thing I'm going to do here is, because I don't want to spend super long waiting for all these, instead of doing 50 inference steps, I'm just going to be doing 20. That's what this 20 is here for. That will mean the quality will be worse, but it will let it iterate faster. So just heads up if the quality is a bit worse on these images. Now that's why. So hopefully we'll get a great anime. Oh, incredible. Oh, good stuff. Not quite as good as earlier, but I'll take it. That's pretty cool. We have our own pipeline working. How can we modify this now? How can we get in here? I want to show you guys some examples. These won't be like the most crazy things ever. We only have so much time here, but I want to get you started, show you how you can get into this and start modifying the pipeline. So what I'm going to do is I'm going to go back up to our produce latents, and I'm going to copy this down here, and we're going to make some modifications. What I want to do is, I'll just tell you what we're doing. There's no reason to keep it a secret here. We want to make a video, and the video we're going to be making is the video from essentially the random noise up to the final image we get. And I think this is pretty cool. You've probably seen this from other maybe GANs, where they start with just noise and they scale up, and eventually they have the final image, and you can see the process of it being made. So the idea, that's the idea here. So how would we go about doing that? Well, what we want is we want to get all of the latents along the path, right? We want to get all 50 latents that are the outputs of the undoing the diffusion, and then we want to run all of those through the decoder to finally get all these frames. Then we can turn all those frames into a video and see the video. Sounds like a lot, but I'm just going to go through it pretty quickly. The general idea, I think, is fairly not too complicated. So I'm just going to add a variable here for returning all the latents, and we are going to then add basically just an array or a list here to track all of our latents throughout all the steps. And at the end of each step, we are just going to append the latents that we have for the step. And then at the end of this, we're going to change this return. So instead of just returning the latents, so long as this variable up here is true, then we are going to concatenate all these latents and return all the latents from all of the steps, as I was just saying. So the next thing we need is we also need to modify this prompt to image function, right? Now that we're giving out multiple latents, we're going to need to be able to handle multiple latents. So we probably don't need to make too many changes, But let's see, what do we need to do here? I guess for one, we're going to need to add in this same thing here, returning all the latents. So when this is true, we'll return all the latents. And I'm also going to add in a just batch size here, because if we try and do all this at once, it will probably overload the GPU. So we'll set this to 2 by default, probably handle more, but better safe than sorry. I want to try and avoid having to restart this whole thing. So now we only have a couple more things we need to do here. One, we need to pass in this return all latents argument. Latents equals, I guess, return all latents. And then we need to change down here how this works. So instead of just running one image or like the whole set of latents through the decoder, we're going to batch it up, put them all in a list, and then return all of those images at the end. So now if we run this function should be adjusted. Hopefully I didn't miss anything here. But we're going to try something like this. I already prepared a prompt. I don't want to take too much of your time now. So we have Starry Night with a violet sky digital art. So we're going to do the prompt to image. Let's do 40 inference steps. It should be good enough. Set the return all latents to true, and now we should get video frames, like a set of video frames, or just really images, a set of images instead of the step-by-step process. So let's do that, and I will be back as soon as that's done. So it's not quite done yet, but I just want to mention, so we did the 40 undoing the diffusion steps, but now we have to do 20 more steps here, and this is because we need to decode all of these 40 images in batches of 2 instead of just decoding this final image this time. So that's why that's there this time. Now that's done though, so what we should be able to do is we should have, let's see how many video frames we have here. We should have 41, so the initial one, and then the 40 diffusion steps. So if we look at the first video frame, it should be, hopefully, just like weird noise or something, right? Let's see what we get. There we go, that's noise, so that's what we want to see. So that's good. What happens now if we look at the final one? This should be the final image. And there we go. We get a starry night. I guess I should have expected from that starry night. I should have expected that. Anyway, now we want to turn these into a video, and I'm not going to go through the code for this. I prepared it in advance, but it's nothing machine learning rated, right? It's nothing like no machine learning stuff. This is just standard Python working with OpenCV to make a video. You can copy these if you want, and they will make a video for you. So very nice stuff here. And the way you use these is you get a video name. So we're just going to take the prompt and turn it into a valid file name. So add MP4 to the end, replace the spaces with something else. Now we can pass into this images the video function, our video frames, the name of the vid, and then we can use this display video function to display this in the window, and hopefully this still works. I just made it a couple days ago, so I don't know why it wouldn't, and there we go. We get a video. So let's go ahead and try playing it and see what happens. And there we go. So it's short. You can change the FPS here. There's parameters for that sort of thing. And of course you can do this with more steps or less steps. You might get a cooler video if you do more steps, I'm not sure, but I think this is like a good length. You can see at the very beginning things are slowly changing, and at the end I think the scheduler might ramp things up to sort of make sure you get to the final image fast enough. But yeah, so this is one example of a way you can mess with this. So the next thing we're going to want to do here, this is going to be a fairly simple thing, and it's going to be sort of this feature they have on DALL-E 2, where what you can do is if they have an image you like, you can actually click on it and get a similar image. So how would we do something like this? I'm going to run through this one really quick because it's fairly simple. So first thing I want to do is just get an image, right? Get an image, but we are going to decide on the latents this time. Now, the reason we're doing this, you'll see, but remember I added a latent parameter and I said I'd explain why I have it there later. Well, here's the time. If we have a latent parameter, what that means is that we can pass in latents and reuse those latents, right? So if you reuse the same latents, the same starting latents, you'll always get the same output. So let's go ahead and generate this real quick. So we should get some steampunkish, like sort of airship or something here. Oh, not subscript to goal. Oh yeah, that was a mistake. Let's just go ahead and do this because I don't want to rerun that. Okay, so interesting. Oh wow, yeah, it's coming down from the cloud. That's kind of crazy. I like this. This is nice. So what would happen if we were to rerun this? I can promise you I'm not going to run it because I don't want to, but we would get the same image as long as we commented this out and reuse the same latents. So the question now is, how can we change this into a slightly different image that's kind of like this? Well, instead of using the exact same latents, what we can do is we can change them up a little bit and then get out a different image. So right here, I have a function that will do just that. It will slightly perturb latents based on how much we want to change them. So you can look through this. It's just standard Python. It's nothing too complicated. And what we want to do is we want to get new latents by perturbing our previous one. So let's start with a very small value like 0, 0, 1. This is going, and this is on a scale of 0 to 1. So this is going to do almost nothing. We should expect almost the exact same image, if not the exact same thing. So let's go ahead and do this. We're passing our new latents this time, and we should get out almost the same image. So hopefully this works. And then what we're going to do is we're going to ramp this up and see how it changes. Oh, wow. Wow. So even with just 0.001, you can already see we're getting quite a different result here, which is pretty neat. You know, I wouldn't expect such a different result from such a small change, but there you go. So we can start ramping this up now. We can go to like 0.1 and we can see what we get. So this should be a bit more different. I'm actually surprised by how different that was already, but let's see. And yeah, that's good, a good bit different. And you know, we can keep ramping this up, go to 0.4 say. This might get a little bit weird because we're not preserving the like standardization of this. Oh wow. Okay, so we still get the same sort of you know, it's still the same prompt, so we have an airship, but it's almost completely different at this point, right? Maybe there's some stuff at the bottom, there's some clouds, but on the whole it's quite different. So you can see this would be one way you can mess with sort of how you use this to get out different results. We're going to do the third and final thing now, the image to image. I know maybe some of you have been waiting. I think this is pretty cool. And this is the previous two things that we did, right? They weren't changing what was actually happening within the model too much. They were kind of using it in a different way. Now we're actually going to be changing things. The idea here, just to remind some of you, we're going to start out with maybe a poor drawing. Like let's say you draw something very poorly. You know, if you're a poor drawer, me, but you want to make something really cool, maybe you draw like an outline, like kind of rough sketch, then you could put it into something like this and maybe improve the quality of your image by giving it a prompt that tells it what you want it to be. And then on top of telling it what you want it to be, you know, having it go through these diffusion steps and actually produce something like that, but something that's still similar to the original image. So how would we do that? Well, first step is, of course, we need to start out with an initial image. So let's start out with like a house poorly drawn by a child, right? The idea here, now you don't need a poorly drawn image. You can do this with anything, but I think this will really show the point, right? If we turn this into something much cooler. So that definitely hit the mark. So how are we going to do this? Well, the first thing we're going to need to do is we're going to need to re-encode this image, right? Because we're assuming we did not get this. Now, we did get this image from our diffusion model, but if we didn't, if we just want to take like a random image we drew, the first thing we need to do is convert this into the latent space so that we know, you know, so that we can work with the latent of this image. And the way we do that is essentially we're just doing the reverse of the decoding process. So if you go back and look at the decoding images function for that, you'll notice that it's almost the exact same as what's happening here, but in reverse order. And instead of decoding something, we're using the VAE to encode it. So what this is going to do is it's going to take an image. I'll copy this. I can show you this in practice. It's going to take the image. It's going to convert it into image latents. Now these image latents, we can then pass back into our decode function. And then hopefully we should get out, if this worked well, the exact same image. Yes. So we're encoding it, we get the latents, decode it, and we have the original image back. So we have a way of going between the original image and the latent space now. And now that we have that, we can work with these latents. So the next thing we're going to need here is a new scheduler. Now I mentioned this, I don't understand exactly how some, I should leave that. No, I don't need to leave that there. I mentioned I don't know exactly how some of these schedulers work, but I do understand the reason we need a new one here. And the reason why is because this specific scheduler we were using earlier, where is it? You know, this one we were using over here, what it requires is that, or the way it works, one of the ways it partially works is that every time you calculate a new image, it stores the last few images so it can kind of get the trajectory that you're going in. The issue with something like this is that we are not starting from like a random latent space, right? As we were before, we're starting from the latent space of this image, which means if we start trying to undo the diffusion process from this latent, we don't have that previous trajectory up to that point. There's like a huge gap there, right? So the previous scheduler is not going to work well for this case. So we're going to use this scheduler instead. It's actually a much simpler one that requires much less work, which is nice. You might ask, why weren't we using this earlier? And the reason is very simply, it doesn't work as well in general, but for this simple case, it happens to be a better fit. What we are going to do is produce latents. Let's go back up here and let's go grab all of this. We're going to rewrite a small portion of this. So this is the code that takes in the text embeddings and gives us our latents. And we are going to want to make a few changes. The first thing, add a new parameter, start step. So we are going to pretend, we're essentially going to, I should explain what's happening here now. Once we have the latents for this image, we're going to add some level of noise. Not too much noise that we completely overwhelm everything and it's just complete noise, but some noise so it's like it's not done being generated yet. We're essentially going to turn this into a half-done image. And then from there, we're going to give a new prompt, not the old prompt, but a new prompt, and then have the model redo the undiffusing process from about halfway into the process. And then essentially that will adapt this image into whatever the new prompt is telling it to go into. Hopefully that made sense. If not, maybe as we go through the code, it will make a bit more sense. So the start step will be essentially we'll be pretending as if we're already 10 steps into the process of this and want to generate a new image from there. So if we have 50 guidance steps and we're starting at step 10, we would have 40 steps left, starting with a version of the latent state of this. Now I say a version of that latent state because we are going to want to noise it up a bit, right? We don't want to start with a finished image when we're only halfway into the undiffusing process. That will kind of mess things up. We need it to be as if it's actually an image or the latent state of an image at step 10. So we're going to need to add noise to the image to achieve that. So the way we do that, I'm just going to copy from here. First of all, this stuff that we needed, this adding the sigmas and all that multiplying, I'm just going to get rid of that. That is not required for this scheduler. That was only for the last scheduler. And then I'm going to add this. So we set the time steps like before. And then if we're above time step 0, start step 0, so we're doing the image to image, what we want to do is get the time step of the current start step. So this is kind of confusing, but essentially this is we're essentially mapping this 10 right here, starting at step 10 to the time step among the because remember what this scheduler is kind of doing is it's converting our 50 inference steps into where they should be along the line of the 1000 training steps. So maybe if we're starting at step 10 instead of step 0 out of 50 inference steps, this would be like in the training process around step 200 because 10 out of 50, multiply that by 1000 training steps, you get around 200. Anyway, we're getting this time step because the scheduler has a way to add noise to our image. So we can add noise to the image as if it was at that time step. I'm not sure if that was a great explanation. Maybe it was a bit too fast, but the TLDR here is we're adding noise to the image so that it is as if it's starting at whatever step we're putting in here instead of the original step or step 0. So that's what's happening. Sorry if that's a terrible explanation. I understood this just by looking at the code for this. So that's something you can also go do if maybe you want to do that. It's all open source under the Hugging Face Diffusion diffusers library. So you can go check that out if you're interested. Other than that, we're doing mostly the same thing here. I think there's one difference we want to do down here, and it's that this scheduler, this step, takes in this time step, which is like the 200, right? The scale of 0 to 1000 instead of the scale of 0 to 50. So it takes in the training step, not the inference step. Just a minor difference there. How do I know that, you might ask? Again, I just looked at the code. You can tell if you go take a look at it. I want to say that's all we need to do for here. Hopefully I'm not missing anything, but then we're going to need to come to this prompt to image, and we're again going to need this start step. And we can set this to like, I don't know, 0 by default or something. And then pass it in here. Start step equals start step. And then I think that's really all we need. It's not too complicated. Hopefully I'm not missing anything. What we want to do now is give a start step. So say maybe start step 7. So 7, maybe if we're doing like 7 out of 20, this would be like 7 steps into the process. So it's still fairly noisy, but they're starting to get some shape there. So instead of rendering a child's like drawn house, now let's render a luxurious house, Unreal 3D render. So hopefully this should transform the house we had before into, well, this new house. So do we have the latents here? I deleted it, didn't I? I did delete it here. Let me undo this thing I did earlier. I meant to keep this. Image latents. So these are the image latents from this image. So we can pass these into here. And now we're going to start at step 7. I don't know why I don't just put a 7 here. Let's do that. So essentially what's happening, getting the images, the latents from this previous image, then we add some noise. So it's as if it's going back into the 7th step. So it's going to be pretty noisy, and then we're going to essentially recontinue the I don't know what it's called. I should probably do this denoising step from there. I think that's what it's called. But with this new prompt that will hopefully make it look like a luxurious house. But oh, Oh, on the very last part of this. So this will happen probably when you're working with this. I'm not sure if it's because of a memory leak or just because of we've made some other things. We're just going to need to restart this and rerun everything to get back some memory. We're just going to need to restart this and rerun everything because we've created like too many images or something that are still stuck on the GPU. So we need to refresh that memory, rerun everything, and it should work. If you get this image, that issue, that's how you fix it. So I'll be right back after I have rerun all of this. Okay, looks like we're almost done rerunning all of it. And by the way, you don't need to re-download anything, so no problem there. And we are regenerating our house poorly drawn by a child. So let's see what we get. Oh, Jesus, that is terrible. Even much worse than last time. Good, good. So we want to turn that hideous atrocity into something good. So this time we just need to make the image latent, get our scheduler, rerun our functions here, redefine them. And now hopefully we should be able to run this, yep, smoothly. Awesome. So let's see what we get. Hopefully something good. Oh, interesting. I think there's an issue here though, right? Because we did 20 diffusion steps, but really we should be starting from diffusion step 7. So let me go back up. I think I might have missed something here. And it looks like indeed I did. We're going to want to start instead of from the initial time step, from the this time step, whatever time steps. Is that? No, sorry. Start step is what we want. The start step we pass in here. So then we don't start from the original thing. Now, I'm not sure how much that actually affected the outcome there. Let's try regenerating it. And this time we should only do 13 steps because 20 minus 7, right? 13 left. Okay. And not the best thing I've ever seen. So here's what I want to do. Let's maybe try something else. So maybe what are two things that are kind of similar here? Maybe we can do Squidward word from, or no, let's just do a squid. A teal squid, and we can try and turn it into Squidward from SpongeBob and see what happens. This sounds like an idea that could not possibly go wrong, right? Oh wow. Let's do a photo of a squid. A photo of a squid. And then let's maybe do 50. This is the last thing we're doing, so I'll do 50 steps for you guys. We can wait it out. I'll be right back when this is done. Oh, jeez. Our photo of a squid here is not nice. Oh, you know what's actually happening? We're using this new scheduler, which is, I mentioned, it's not as good in general, right? So let me go back to the old scheduler. I'll redo this until I get a decent image. I'll go back to the old scheduler and redo this a couple times, or maybe just once or twice. I'll be right back. Okay. I only used 30 steps, but I think I got something I'm proud of. I think we can turn this into Squidward, right? Like, what could possibly go wrong? So, let's just rerun this, grab those image latents. Oh God. Oh Jesus, just look at it. This is going to be great if we can actually turn this into Squidward. The issue is I'm not sure this, the training set is probably less data than there was for DALL-E 2. I'm not sure if we're going to let's just do Squidward. I'm not sure if it knows who Squidward is. So 30 steps. Let's start from step 7 and let's just see what happens. Hopefully something not too atrocious, but you never know. I guess we'll probably figure out if it knows what Squidward is pretty quickly. Oh, geez. So you can see there's similarities here, right? Let's maybe, so if we make this, if we start from an earlier step like 2, this is going to add so much noise, it will be like this is almost completely noise. So this should give us something that's completely different almost from the original image, but not completely, but almost completely. Oh, Jesus. That is terrifying. So I'm guessing there's no Squidward in the, or not enough Squidward in the training data set. So it's just, this is what it would think Squidward would look like if it didn't know what Squidward was. But if we go do something like 25 now, this is already almost done generating. So we should get something very similar. Yeah. So you can see there's not many differences here. And then we can kind of scale it. So if we do 20, we get something a little bit more different. Oh, wow. It looks like I have reached my maximum duration. I think so many people have been using Stable Diffusion recently that they've started putting in more restrictions, unfortunately. Tis a shame. I guess I'm contributing to that now. But anyway, yeah, I really don't want to rerun this whole thing. So I'm going to say, I'm going to link all these things down in the description if you want to use them. I hope this sort of thing has taught you a lot about how this works, about how to use this, about how to do this and that, your opinions about this versus DALL-E 2, all of that. Anyway, if you like this sort of thing, consider subscribing. It really does help out the channel. Super appreciate it. Anyway, it's 4 a.m., so I'm going to head to bed. Thank you so much for watching, and I hope to catch you next time.